It's a pleasure to have Tomer Ezra visiting us from Harvard. Tomer is currently a postdoc at Harvard, work on mechanism design, contract theory, sort of algorithms with limited information more generally. And Tomer got his PhD in Tel Aviv. Then Michal Feldman, since he has been in Rome in the Sapienza for a postdoc in the Simon Laufer Mathematical Institute, and right now in Harvard. Tomer has been pushing the boundaries of what we know about contracts, and it's a topic that is immediately we're interested in. It's quite used inside in here. So I think to be a very interesting talk for us to learn from you. So please take it over.
Okay. So hi everyone. Thanks for the introduction and thanks for having me here. So today I'm going to talk about algorithmic contract design. So contract design is a topic that studies how we should incentivize people to do that effort. And today we're going to look at it from an algorithmic point of view. Okay. So in general, contract design is one of the pillars of microeconomics, and the basic question that it tries to answer is how we incentivize people to work. Okay, it captures many real-life scenarios. For example, when a company hires influencer to promote its products, when an employer designs incentives like bonuses to the employees, and when you hire a real estate agent to sell your property for a commission, percentage-based commission. Okay, so let's dive a bit deeper into the first example, and let's say that Nike launches a new product. In this case, a new model of shoes, and they want to sell it. And for each pair that they sell, they earn $10. Okay. Now, to promote the product, what they do is they hire an influencer that can promote it to its followers, by in social media. Okay, the way that they interact with this influencer is by offering them a contract. Okay, and a contract can take many forms. One simple option is just to offer a fixed amount, let's say $1,000, for telling the influencer you should post several posts on social media and promote the product. So the issue with this approach is that once you fix the contract, now the influencer has no incentive to do a good job. He gets the money no matter what. And even if he satisfied the condition of posting several posts, he will not have incentives to put in it effort, and that will really promote the product. Okay, so an alternative approach is to offer a payment based on outcomes. Okay, so this is actually what usually these companies use for this thing. Instead of fixing the amount you pay, you pay in correspondence to the influence that the influencer does. Okay, and then the question becomes of how much should the Nike should pay the influencer per each sale that the influencer gets. Okay, on the one hand, if they pay too little, the influencer will not be very motivated and will just will not put a lot of effort, which will lead to fewer sales. On the other hand, if Nike will pay a lot, so the influencer will be very motivated and will put a lot of effort in promoting the product. However, Nike will only have only a bit of the revenue. Most of the revenue will go to the influencer. So this is the type of questions that contract theory try to model, analyze, and solve to find the right trade-off between not incentivizing enough and not paying too much. Okay? But this example is very simplistic illustration of what Nike really wants to solve. In real-life scenarios, the influencer has many options of what she can do. She can promote it on Facebook and Instagram, and she might have an intersection between the groups that she can interact in each of the in each of the platforms. And moreover, Nike doesn't want to hire just one influencer. Nike wants to interact with multiple influencers. Each of them has many options of how to promote the product, and that might intersect or not. And this is the type of questions that we are going to look at today to analyze and to try to model that. Okay? So questions so far? Okay. So before presenting the models that we're going to see today, let me tell you about my research. So my research on contracts tries to capture these complexities. Okay, so I study extensions of classic contract models for different dimensions of complexities. In particular, when the agent has many actions that they can take, for example, promoting it on Facebook, Instagram, TikTok, and maybe 100 more options for the actions that they can take. A second dimension of complexity is what happens when the principal interacts with many agents. A third example of the dimensions of complexity is what happens if Nike now wants to sell multiple items. And like promoting like a bundle might be cheaper than promoting just each one individually. Okay, so these are the type of questions that I ask in my research, and today we're going to focus on the two first dimensions, like multiple actions and multiple agents. Okay, and in particular, we're going to see two models. So in the first model, we're going to see a model for a principal that wants to incentivize an agent to take actions, and the agent can take many actions in order to complete the actions, and can actually take any combination of actions to complete the task. So this will be the first part of the talk. In the second part of the talk, we are going to see a model of a principal that wants to incentivize multiple agents simultaneously, that the overall outcome is influenced by actions of all the agents. Okay, so let's start with the first model of the principal incentivizing a single agent taking multiple actions. This is based on two papers, one in Fox 21, one in ITCS 24. So before I go to our combinatorial model, where you can take many actions, let's see how classical contract theory model the principal agents. So we have like the initial models that we start with. So in the classical contract theory, like we have two entities, a principal and an agent. The principal wants to incentivize the agent to do some task. So in the example, it was Nike that wanted to incentivize the influencer. Now, the agent, in order to complete the task, can choose one action among a predefined set of actions. Okay, and each such action is associated with a cost that incurred by the agent, and also associated with a reward that goes to the principal. So you can think of it as the effort that the agent put in doing the post, and how much is the expected revenue that the principal is going to get from this amount of effort. Okay, now so far we didn't if this is the entire model, like the agent has no incentive to exert effort. Okay, like he's incurring all the cost, while the principal receiving the entire reward. So in order to incentivize the agent to take an action that will lead to a good outcome, the principal can offer a contract. So in this model, a contract is just a single number between 0 and 1, which is what is the fraction of the reward that the agent is going to get at the end of the process. Okay? So the principal can offer a contract, and then now the agent has both negative incentive. Like he still incurs the cost, but he will get payment that depends on this contract alpha. Okay. Now the utilities of the entities in this model. So let's start with the principal. So the principal utility is the fraction of the reward that remains with her, which is 1 minus alpha, because she pays a alpha fraction, times the reward, f of I. And the agent's utility is the payment, alpha times f of I, minus the incurred cost, c of I. Okay? And the goal of the principal is to find a contract that will maximize their own utility, given that the agent will best respond to this contract. The agent maximizes his own utility, and the principal, given that the agent tries to maximize his own utility, the principal wants to maximize her own utility. Okay, so this is a simplified version of a classical model of contract theory. Questions about this model? Okay, so what we do in our research, in a paper with Paul Nutting, Michael Feldman, and Thomas Kesselheim, we introduced a combinatorial version of this model, in which we introduce two changes to this model. So the first change is that now the agent does not select just one action, it selects a set of actions. Okay, it selects a subset S that is subset of the entire set of actions. Okay, so he has many more options of what set to select, not just if there are n actions. So now he has 2 to the n options of what he can select. And of course, this influences the entire stream of occurrences. So the reward function is now a combinatorial function of the set of actions that the agent takes. We are going to assume in the stock that the cost that the agent incurs is the sum of the cost of the actions that it took. So if it takes actions 1 and 2, it pays the cost of action 1 plus the cost of action 2. And you can adjust the utilities accordingly. Okay, so this is the first change that we introduced to the model. And the second goal, because we want to study it from a combinatorial point, from an algorithmic point of view, we want to not just find the contract that maximizes the principal utility, we want to do it efficiently. Okay? And why this change is important? Because if we forget about efficiency, what you can do is just ignore the combinatorial structure of the model by imagining that you have an instance with 2 to the n actions, let's call them meta actions, an action for each set, and you can just rewrite the problem as the original contract problem. Okay, but if we care about efficiency, this modification will increase the size of the instance exponentially, and in the end, we want efficient algorithm that run in polynomial time. And when I say polynomial time, I mean polynomial in the number of actions in the original instance. Okay, so whenever I say in the stock polynomial time, I want it to be polynomial in the number of actions of the instance. Okay. Questions? Okay. How do I?
I'll just talk. So is the reward of the production function like arbitrary? We're dealing with any possible f as a function of the subset of actions chosen.
So we're going to see it in the next slide. So we're going to now formalize. So this is like a non-formalized version of the model. Now we're going to see like we're going to formalize it. Okay, and we're going to mention what we assume about the reward function and so on.
I got it.
Okay. Okay, so let's see the formal model. So again, our formal model for the analyzing this type of problem is we have a set of actions, a set of n actions, number 1 to n. Each action is associated with a cost, non-negative cost, and we assume that the cost function is additive. If the agent takes a set of actions S, it pays the sum of the cost of each of the actions that it takes. Now, on the other hand, for the reward function, we are not going to assume that this is an additive function. In general, it will be a combinatorial function. A combinatorial function, it means that it maps each set of action to a non-negative number. And the principal needs to output a linear contract, which is a number alpha between 0 and 1. And so one question that might arise is like, why focus only on linear? Why don't do something more complicated? Like if the reward is at least something, you pay something. So there are two main reasons to focus on linear contracts. One is that this is a class of very natural a class of contracts that is well used, well studied, like very simple to use, very simple to implement, and we see them a lot in real life scenarios. So it's interesting by itself to study them, to study what you can achieve with linear contracts. And the other reason, which I'm not going to get into in this talk, is that there is a very nice hardness reduction by Duting, Ravgard, and Targam Cohen that showed that under like a bit more general model that I will not get into the details, like linear contracts are like every hardness result that you have for linear contracts in this model will extend to nonlinear contracts in general, to honest result for general contracts. Okay, so basically, if we show that something is impossible in this model for linear contracts, it is also impossible if we remove the assumption of the linear contracts. Okay, and the same holds with respect to approximation. And our goal is to ask, can we find, a recent question is, can we find the optimal linear contract in a polynomial time? And in cases that we cannot, can we at least get a good approximation of it? So you mentioned, you asked about what do we assume about the reward functions. So we are going to study this problem for under various assumptions on the reward functions. So we look at the complement-free hierarchy of set functions introduced by Lehmann and Wilson that categorize the set of combinatorial functions to level of complexities. So the simplest version is basically additive functions, where the reward of actions 1 and 2 is just the reward of 1 plus the reward of 2. And as we go like to a broader circle in this diagram, we get a more general class of valuations. Okay, so I'm not going to define a class of reward functions. So I'm not going to define the entire hierarchy, but today we're going to focus on the interesting case of some modular reward functions. Okay, so let's define what is a modular. So some modular functions are functions that have the following nice property, that as you add more and more actions, each action contributes less and less. Okay, formally, if we take two sets, S that is subset of T, and now we add action J to the smaller set, it will increase the reward by at least as much as if we add it to the smaller set T, to the larger set T. Okay, so this is a very nice property, and this is a property that we expect to see in many settings. In particular, like the example in the beginning for the motivation of the exposure. So the amount of people that see the promotion is called a coverage function, which is a special case of some modular functions. Okay, so this is the focus of today's talk. And the last thing we need to define, like to mention about in order to finish the formulation of the problem, is how do we access the reward function? Because usually when you deal with combinatorial functions, you don't assume that you get a string of bits that describes the function, because these descriptions has an exponential size. Okay, instead we said we want algorithms that run in polynomial time in the number of actions, so don't want to go over the entire function. So what we do is we assume that we have a value oracle to we assume that we have oracle access to the function. Okay, so the first natural oracle that we consider is called value oracle, which is given a set S, what is the reward given that the agent takes this test of action. So given S, we can access the value f of S. So this is the first oracle. And the second oracle that makes sense in the settings is a response oracle. So this is a bit more complicated, and you can think of it as, given a specific contract alpha, can we get the set of actions that maximize the agent utility? So basically, you can think of it as we offer some contracts, see what the agent does, and see the response of the agent, and continue and can change now to a different contract. Okay? So this is the second oracle.
So we can maximize this modular function essentially. Why does the linear function?
So I assume that the agent knows what's best for him. So if it's a submodular, yes, I assume that he knows to solve this specific submodular case. But in general, our main result for this will be for gross substitute. But
for gross substitute, you get the polynomial time plus value oracle.
Yeah. Okay. So more questions about the model? Okay. So now that we formalized our model, let's go to our results. So our results for the case of a single agent. So again, our research question is, can we find the optimal linear contract efficiently? Or in cases that we cannot find it, can we at least approximate it? So our first result is that for the class of gross substitute reward functions, which is a subclass of submodular, we can find the optimal contract in a polynomial type using only value OLK. Okay, so this is our first result. Now, if we go beyond gross substitute, let's go, for example, if we go to the next class in the hierarchy of submodular, if we have only value oracle, not just that we cannot find the optimal contract, we cannot get any constant approximation. This problem is spawning out, and we cannot get any constant approximation. So we have a sharp separation between the class of gross substitute and the class of submodular. Now, if you allow the algorithm not just to have value oracle, but we give the algorithm both value and response oracles, we show that although we cannot find the exact optimal contract, we can get a FPTAS, which means we can get a 1 minus epsilon approximation. We can find an algorithm that guarantees 1 minus epsilon fraction of the optimal contract in time that is polynomial in the number of fractions and in the epsilon. Okay? And in a follow-up paper by Duting, Feldman, Galtzu, and Rubinstein, they showed that theorem 3 is tight, in the sense that finding the exact optimum is actually hard and requires exponential time. Okay, so this is our main results for the model. Do you have questions? Okay. So let's see a bit of the techniques and the ideas behind and the structure behind this problem. Okay, to do so, we are going to consider a very simple case of additive reward functions with the following numbers. So we have 3 actions, 1, 2, and 3. Action 1 has a expected reward of 3, action 2 reward of 2, and action 3 is 5. And again, this is an additive function, and the cost function is also additive. This is an assumption of the model. Okay. Now let's assume that the agent decides to do action 1, no matter what, decides to take this action. Okay. So how does the agent's utility look like as a function of the contract? Okay, so on the one hand, if we offer a contract of 0, then the agent will get 0 times the reward of 1, which is 0, and we pay the cost. So we'll get a utility that is minus 1. We just pay the cost. On the other hand, if we offer a contract of 1, which means that we pay everything to the agent is going to get 3 minus 1, so you get a utility of 2. And everything in between, it will get the affine function that intersect between that lines between these points. Okay? Now, what we can do is we can write the affine line of the agent's utility for each subset of actions. So we have 3 actions, so we have 8 potential subsets of actions that the agent can take. Each one of them defines such a line. Okay? So if we draw everything on the same graph, we get to the following picture. And now let's look at the problem from the other direction. Now, instead of fixing the actions that the agent takes, let's fix the contract and see what happens. So if now the principal fixes a contract of 0.6, so what the agent does, he looks at this picture of all the utilities from all the different sets, and he takes the one that has the highest utility, which is the one that lies on the upper envelope. Okay? Now, what we can do is do it for every point in the interval of contracts between 0 and 1. And this gives us a partition of the interval 0, 1 to sub-intervals in which the agent takes the same set of actions. Okay, so here, between 0 and 1/3, it takes nothing. Between 1/3 and 1/2, it takes action 1. Between 1/2 and 0.8, actions 1 and 2. And above 0.8, you get actions the 1 to 3. Okay, so this is the agent's utility function. This is how we construct the agent's utility function as a function of the contract alpha. And as we can see, this function behaves really nicely. Like it's continuous, it's monotone, it's convex, and it's very easy to prove these properties. So this is the agent utility function. Now let's go to the principal utility function. So the principal utility function for this example behaves like this. So as you can see, the function is always decreasing, except for points in which the agent changes the best response. Okay? So as you can see, this function is not continuous, not monotone, and it's much more difficult to analyze. But one simple observation that we can make is that if you look at the points in which the agent changes the best response, which return these points critical alphas, then one of those must be the optimal contract. Okay? Because the function is always decreasing as long as the agent doesn't change the best response. So the optimal option for the principal will be to offer a point that is immediately after the agent changed the best response. Okay? And this gives us the following approach for solving the case of cross-substitute functions. So we do this by the following simple approach. So our algorithm is just go over all critical alphas, calculate the principal utility for each one of these critical alphas for this contract alpha, and return the best one. Okay, although this is like the first thing that comes to mind after you see this result, like after you see the structure of the principal utility. However, implementing this algorithm is a bit more complex. It requires three parts. So we need to be able to iterate over the critical alphas. Like this is not something that is given to us as part of the instance. We are given a function with Oracle access, and we're given the cost, and we need to find these critical alphas. The second thing we need is to calculate the principal utility for a given contract. And the last thing is we need that for this algorithm to work, we need that the number of critical alphas to be not that large. We need, for example, if we want a polynomial time algorithm, we need that the number of critical alphas will be polynomial. Okay, this is a must-have property. Okay, and what we show is that we can iterate over the critical alphas for the case of gross-substitute reward functions. In general, calculating the principal utility for a given contract can be implemented by a response oracle in general, and specifically for the class of gross-substitute, this can be reduced to value oracles. And the most technical part is to show that the number of critical points is bounded, and we show that for the class of gross-substitute functions, there are at most n squared critical points. So this is why this algorithm, we can implement this algorithm and find the optimal contract for the class of gross-substitute. Okay, so questions?
For the bound critical alphas, we're going to discuss next.
So I'm not going to. So this is
simulating the greedy algorithm, like simulating the greedy algorithm, and see how many times it swaps from one item to the other one.
So what we do is we analyze what happens in a change. So one of two things might happen: either when you increase the payment, either the agent will add another action to the best response, or it will replace one action with another. And you have this property that you must replace it with an action that has a higher cost.
Okay, then it's a monotony that we can use.
Yes, and then you can create kind of a potential function argument and show that the number of steps is bounded by a quadratic number. And yeah. Okay. So,
and wait, one question: have you looked at this gross substitutes as multiple copies, or
of what?
Gross substitutes is like with copies. It's like
what do you mean by copies?
Gross substitutes is like potentially if the actions they also have integer values. Like Usually graph substitutes is a function of the hypercube, like include each action. But you can also imagine like you put a number to each action. You can take 2 of action 1, 3 of action 2, 4.
I think it maintains the property of
property, but I see. And it becomes quadratic in the sum of.
Yeah, the sum of the size. I guess the sum of the sizes, but yeah.
Right. So like going beyond number of copies, so can you do like let's say continuous? Like suppose I have multiple resources, and each resource like you need to take like continuous effort. So maybe that also works.
Yeah, that's actually a good point.
So yeah, so we try to avoid like continuous version because in the end we wanted to have like notions of complexities of discrete optimizations. I agree that it's like there are other people that are working on a continuous version of this problem, and like some of the analysis translate, some not. But indeed, this is a very interesting direction.
Generally, a quick comment on the question about you could take the same action multiple times. I think you would either just take all the copies or none of the copies for the given contract. Unless
I didn't hear the last part.
Oh, is it not the case that you would just take all copies or no copies?
No, not necessarily. Ghost substitute might have like in additive, yes. Okay. In Ghost substitute, you might have you always increase the number of copies that you take from a certain type, or replace from one type to another type with a higher cost. But in general, you will always increase kind of the potential that we mentioned earlier. Okay, so this concludes the first part of the talk. Now let's continue to the second part of the talk. We'll talk about a principle that wants to incentivize multiple agents. Each of them can take many actions. Okay, this is based on 2 papers, one in Stock 23 and one in Soda this year. Okay. So let's start with the model. So again, this is a paper with Paul Dutting, Michael Feldman, and Thomas Kesselheim. We have n agents. Each agent now has AI, the set of actions that he can take. And he can take, again, a subset of actions. You can take any subset S of AI. And for simplicity, without loss of generality, you can assume that the sets of action of the agents are disjoint. And again, we are going to assume that the cost functions are additive. Like if some agent takes actions 1 and 2, it pays the cost of both the actions. And now the reward function is a combinatorial function of all the actions of all the agents. Okay, so it's a mapping from all subsets of the union of the actions of the agents to a non-negative number. Okay, and again, we're going to assume that it belongs to the hierarchy, complementary hierarchy of combinatorial functions. One very useful notation that we're going to use in this talk is given a set S, we are going to denote by Si the projection of S to the actions of agent I. So it's just the intersection with agent I, with AI. Okay, and our goal is to find a contract, which is now not just a single number, but now it is a vector, alpha 1 to alpha n, which is and alpha I is the function of the reward that is going to be given to agent I. Okay, so our goal is to find the vector of what is the function, how to allocate functions of the reward in order to guarantee good utility for the principal. So questions about the multi-agent model? Okay, so one thing that is not fully defined in this slide is what do we mean by guarantees good utility? Like in the single agent case, it was very clear. Once you offer the contract, the agent is going to do the best response, and we can calculate what it is, even if it's complicated computationally. Like in general, there is a best response for the agent, and this will give us our utility. Now, when we consider multiple agents, once we fix the contract, now actions of one agent might influence the actions that another agent want to take. Okay, so what we do in this case, we study this from a game theoretic perspective. Okay, so we call it the agents game. Okay, so once we fix the contract alpha, the agents play the following game. Each one can select a subset of actions, Si among is a set of actions, AI, and the utility of this agent is just the fraction of the reward of all the sets of actions that the agents decide to take, and they pay the cost of their own actions that they selected. Okay, so it's alpha times the reward minus C of Si. Okay, and usually, like this type of games are analyzed using a notion of equilibria, and specifically we're going to consider the case of pure Nash equilibria. So what is a pure Nash equilibria for this game? So once we fix the contract, so a profile of action, of sets of actions, is a Nash equilibrium with respect to contract alpha. If no agent want to deviate from his set of actions to another set of actions, which means that it's basically a stable state. No agent want to change his profile of action. This is the thing that given that we fix the other agent's actions, like this is the best response of for him. Okay. Now, Nash equilibrium is a very nice property for games to analyze, but in general, it might not exist it doesn't exist for every game. Okay, so the first thing we show is that for this type of game, no matter what is the reward function, and no matter what is alpha, there always exists a pure Nash equilibrium for this game. Okay, so this game always has a pure Nash equilibrium. It's always well defined. There is at least one for each contract. Okay. So now what we can do is we can denote the set of pure Nash equilibrium that correspond to a specific contract alpha by NE of alpha.
So Nash equilibrium exists for F gross substitutes, so in general?
In general, no matter what is the reward function. Okay.
Is there any easy to see like why Nash equilibrium? Is that non-trivial to prove that?
It's few lines proof. It uses a potential function argument. Like there is a potential function game. Yes. Ordinal potential function game. Define an ordinal potential function. Okay. So now that we have this observation that we have Nash equilibrium, we can now define our benchmark. Okay. So what is the best thing we could hope to achieve in this game? Okay, in this settings. So the optimal thing we can hope for is the following definition of UP star, which is the supremum over all vectors of contacts, alpha. And we take the best equilibrium with respect to this contact, and we take the utility of the principal for this contact and this profile of and this Nash equilibrium. Okay, so this is the best thing we could hope to achieve. So this is what we define as our benchmark. And the question that we ask is, can we find a contact alpha that guarantees that no matter which equilibrium we get that corresponds to this contract, we get at least some, let's say, concept approximation to this benchmark that we define. Okay, so can we find it? And we want a very robust guarantee that not just in some equilibrium, we want in every equilibrium, our contact will behave nicely. Guarantees the concept approximation. Okay. So this goal is very ambitious and raises like several challenges. The first challenge is that we said that an equilibrium might always exist, but there might be multiple equilibria with respect to the specific contract. Okay, so it's not clear that our goal is achievable, and even worse, the gap between different equilibria of the same contract can be arbitrarily large. Okay, you can have unbounded gap between the utility for the principal under one equilibrium and another. And even worse, both of these challenges appear in the contract that defines the benchmark. Okay, there are instances in which the optimal contract that defines the benchmark has many equilibria, and one of them is it gives terrible utility. Okay, so it's not clear that we can achieve this goal. Okay, so now let's move to our results. So again, a research question is: can we find the optimal linear contract in a polynomial time, or at least get some approximation? And we're going to do it for the complementary hierarchy under the both models of value oracle and value response oracles. So our first result, that even for the simplest case in the hierarchy of additive reward functions, okay? So it means that the simplest case where the reward of the expected reward of the principal as a function of the actions that the agents take are additive, we cannot find the optimal contract in polynomial time.
So sorry, just one question. If everything is additive to value in the contract, doesn't it decompose across agents? So what's the relation between different agents? If it's
so the given a contract, like I don't care what you do to decide what I do, but I still get a fraction of the entire reward.
I get a fraction of what everyone else.
Yeah,
and not only on your contribution.
So we only study here like linear contracts in which you get a fraction of the entire reward.
Mm-hmm.
So this is where you have a connection between the different agents. Okay.
So people study this version of you get a fraction of your marginal contribution or something like.
So I have now a project that tries to define this. It's a bit difficult to define it. It's not defined for every class of functions, and you need to be very careful with this. And also here I'm presenting a simplified version. In general, you have like a noisy version of the function. You don't observe the function. You for example, know the.
But then you have no notion.
Yeah, you don't know how to contribute exactly where the reward comes from, and you know only the expectation, let's say, and then you cannot do this type of things.
Makes sense.
Okay. Okay. So you cannot find the optimal contract, but instead, what you can do, you can get a one-mass approximation. Okay. So you have a f-pitas for the simplest case, but already here we see that it's very different from the single agent case, and it's more challenging. Okay. When we go beyond that detail, we show that for gross aptitude, you cannot get f-pitas. You cannot get as close as you want. You can't guarantee as close as you want to the benchmark, a fraction that is 1 epsilon to the benchmark. What you can do, you can guarantee a constant approximation if you only have value oracle to the reward function. Okay, so you can guarantee a constant approximation. This is the best you can hope for. Now, we know from the single agent case that if you go beyond beyond gross aptitude, we cannot get any constant approximation. So beyond gross aptitude, if you only consider value oracle, we cannot do anything. Okay, so this is why the case of only value oracle, this is closed, and you can get it only up to gross aptitude. Now, when we add the response oracle, then we show that actually we can extend our positive results to the class of some modular reward functions. So for some modular reward functions, using value and response oracles, we can find in polynomial time a contract that guarantees a constant approximation. This is the best we can hope for. Okay? And if you look beyond the some modular, then again we have impossibility results. We show that for the next class in the hierarchy of XOS, we cannot get, even if you have value on response oracles, we cannot get any constant approximation. Okay, so this is closes the picture. Questions? Okay. So let me continue to the summary. So today what we saw, we introduced models to study contracts from computational point of view.
Maybe, sorry, that's a question first. Like, can you give some intuition of what these contracts look like, or how to find an equilibrium that like is good for everyone? Is there any intuition you can give?
It's for the sum modular. or
Like maybe even for additive, or whenever this problem occurs that you have multiple equilibria, that is an unbounded gap, how to find one thing that's more or less stable. Or any like high level idea?
yeah. So the idea is, in general, our approach is that either there is a very important single agent that we want to incentivize. In this case, we take an approach that is very similar to the single agent case.
Just don't give anything to anyone else. Just treat that as a single agent problem.
Yeah, we try to focus on each agent individually and solve the optimal thing for this. And if there was a very important agent in the optimal contract, like we would find it using similar approach. And this works up to some modular, even beyond some modular. Like, but for this case, it works here. So this is the first case. Now, if you don't have many agents, if you don't have a single agent that is very important, it means that each one contribute very little. Okay, so and our approach is to start with the optimal contract, which is very hard to find because you can hide a really specific structure that like it is a unique something of a weird optimization that you need to do. And now let's start to remove agents. Okay, remove half of the agents randomly. Okay, if you remove half of the agents, you expect because each agent is small, you expect the reward to be half of the reward because of some modularity. But you don't know how to incentivize it. So apparently there is a very nice structure of this problem that if you now you double the payment that you need in order to pay for the agents that you didn't remove, like they will do at least some part of what they did originally. Okay.
Is it the same intuition as Mitra Secretary or no? With half the prices, you double the rewards.
Like I don't see the connection, but
Yeah, it's either I don't know. Either you're paying too much, enough. I don't know. In case,
like I don't see the connection, but yeah.
it is a question, but also
Yes.
Yeah. Do you know what the picture would look like if you had unbounded computation time and the only issue is that you're comparing best equilibrium versus worst equilibrium?
Yes. So there we don't have a complete picture. So some of the results here are because of this this gap. So of course, so for additive, like there is an annoying tie-breaking case that happens already in the single agent, because the optimal contract is when you offer the payment that is like the agent will be indifferent. So theoretically, if you want to consider the worst equilibrium, you must incentivize a bit more, but you can find, if you are not limited computation, you can find this point where up to tie breaking you get the optimal. And the tie breaking is such that it doesn't depend on the other agent. So you get it, you can get for additive basically. But for the case of like the hardest result that we show for gross substitute and for XOS is like for gross substitute, there are instances in which, because of the benchmark, the difference between the best and worst equilibria, you must lose a constant. Okay, so it's unavoidable to lose a constant even if you ignore computational aspects. Okay, and the same holds for XOS. For XOS, there are instances where you lose not just a constant, you lose a factor of n. Okay, you lose a factor of n between best and worst equilibrium, and therefore computation doesn't play a role here. Okay, I would say if you allow yourself to choose the equilibrium, then you still have some hardness results. Specifically, we showed it for some modular. You still cannot find better than constant, and for subadditive, you cannot get better the polynomial approximation, but you might be able to get the optimal contract for gross substitute or a constant approximation for XOS. Okay. Okay. So let's summarize. So today we saw computational models to study contracts. We did it through the following research questions. Can we find the optimal linear contract? efficiently, or at least approximate it. We did it for various assumptions of the reward function, that the function belongs to the complement-free hierarchy under two computational models. Either we have only value oracle to the reward functions, or both value and response oracle. Our work opens many computational problems. For example, what happens if we want to compare? We define the benchmark as the best contract of the worst equilibrium, like to compare ourselves to something that has the same power. Can we get better results? Again, there are several questions that I mentioned earlier about what happens if we can choose the equilibrium. There are open questions for the case of Gauss substitute and XOS. Another approach is like to look at classes of reward functions that do not belong to the complementary hierarchy. In particular, there is a line of works that already looked at different cases. What happens with supermodular reward functions? What happens if we have combinatorial cross functions, etc. And last directions is what happens, for example, if you consider different notion of equilibrium. Let's say a mixed equilibrium, correlated or cross-correlated equilibrium between the agents. That's it. Thanks.
Thank you, Speed. I think you have time for maybe one or two questions.
So do you know if there's any cases where like the best like mixed Nash equilibrium in the game has better utility than like the pure Nash equilibria, or one?
Yeah.
Okay. So
there is a paper like that study this type of problems, like a very special case that corresponds to some modular, a special case of some modular reward functions. I already showed in the early 2000s that there is a gap between what you can achieve in a mixed equilibrium and in a pure Nash equilibrium. So now in a paper that we are working on, we show that the gap is at most a constant for most classes, or up to, I think, for sure for some modular, but I think even beyond some modular. And we have a characterization of what the gap between the best pure equilibrium and the best mixed correlated or cross-correlated equilibrium for both for the multi-agent case. Okay.
Yeah.
I hope to get any result as complements or anything with complements that can be done in the setting.
So when you have complements, so one special case of complements is supermodular. So basically in a paper by Dutingel, Sur, and Feldman, they showed, and another paper that was simultaneously published, they showed that the problem for the single agent with supermodular reward function is tractable, and you can find it in polynomial time. And again, it's a similar approach to what we did, like with going over the critical points, but they have different.
No, it's modular minimization.
It relates heavily to modular minimization. Yes, because modular minimization is tractable, but you have here a very interesting property, like the property that you can solve it for Gauss substitute, not just because Gauss substitute is you can calculate demand queries for Gauss substitute. You need to look how the function changes when, like, you look at this function scaled minus a constant additive function. Okay, and you need the change in this function to behave nicely. Okay, so this is the new part of this.
Yeah. Okay. Very nice. I think over time. So let's thank the speaker again.